Welcome to a webinar series on flow diagnostics. Today's session is laser Doppler velocimetry, fundamentals and applications. This is Sanjit from TESCON India. For over 25 years, TESCON has been providing advanced flow measurement techniques such as PIV, LDV, and high-speed imaging systems for research and development in fluid mechanics. TESCON has been partnering RTM Technologies, providing laser-based diagnostic instrumentations for close to a decade now. Our presenter today from RTM Technologies is a renowned scientist in the field of phase Doppler interferometry technology, Dr. William Bachalo. Dr. Bachalo specializes in space studies, aerosol characterization, cloud and atmospheric research. If you have any questions during the presentation, please type them into the chat box in a control panel. We'll answer the questions after the presentation. Welcome, Dr. Bachalo.
Thank you, Sanjit, for your kind introduction. And I'm happy that you all have decided to attend this webinar. Good morning and greetings to everyone in India. This talk is going to be, as Sanjit pointed out, describing laser Doppler velocimetry. And I thought before I get started, I should try to avoid some possible confusion by mentioning that Europeans generally call this method laser Doppler anemometry, or LDA. They apparently don't understand the meaning of anemometry. Anemometry refers to measuring wind speed. LDV instruments can measure gas and liquid flows as well as surface speed, so we refer to this device as a velocimeter rather than an anemometer. Although this instrument has been around for about 5 decades, it continues to undergo development, taking advantage of recent advances in solid-state lasers, optics, electronics, and computers. The invention of this instrument represented a great step forward in our ability to measure complex flows and turbulence over a very wide range of applications. Before I get started, I thought it would be useful to introduce our company and describe what we're doing in a little more detail than Sanjit provided. RTM was founded in 1998 by former Aerometrics employees. Aerometrics was a company I founded in 1982 based on my invention of the phase Doppler interferometer. At the same time, we continued our work supporting NASA with flow measurements using LDV and holographic interferometer methods. I had done a postdoctoral research fellowship at NASA where I helped develop the LDV method, and so we continued that work. Our team has been together for a long time, since the 1980s, so we're well seasoned, well experienced in this field. At RTM, our main focus is in developing optical diagnostics for fluid mechanics, fuel spray combustion, and atmospheric studies and research. We have been funded generously by NASA, the U.S. Navy, Office of Naval Research, U.S. Air Force, U.S. Army, Environmental Protection Agency, the National Institutes of Science and Technology, and California Air Resources Board. Particles and particle dynamics are a critical part of our work, so we have developed significant expertise in particle light scattering and imaging systems design and development. We have continued to develop the laser Doppler velocimetry and phase Doppler interferometer methods, which are the phase Doppler method, which evolved from the basic LDV method. When I was doing my work at NASA, we were concerned about particle response, which I'll spend a good deal of time talking about in this presentation. And the idea was to be able to measure particle size at the same time as the velocity, and that would allow us to discriminate particles that wouldn't track the gas phase turbulence fluctuations. And so that phase Doppler instrument was successful in doing that, but it does a lot more. We have significant experience in the area of atomization and sprays research associated with a wide range of applications, including spray combustion, medical sprays, agricultural sprays, and industrial applications. The current emphasis of our company is aircraft icing and atmospheric cloud research, and we're providing instrumentation for that purpose. We've also developed the laser-induced incandescence instrument for measuring non-volatile materials or particles in the atmosphere. So as an outline of my presentation, I'll provide a background and features of the LDV instrument. I'll provide a description of the measurement principle in some detail. I'll talk about signal detection and processing, which is a very important component in getting reliable measurements. I'll show some optical configurations and kind of provide information on how one might properly configure the system for various flow challenges. I'll talk about seeding with particles and the particle dynamics which are associated with that approach. I'll discuss particle response characteristics because the LDV method actually measures particle velocities rather than the direct gas phase or liquid phase velocity. So particle response is a critical component in getting reliable measurements. And then I'll give a few application examples if time permits. Well, as part of the background, a critical advance that perhaps led or helped lead to this important invention was the development of the helium neon laser at the Bell Labs in the United States in 1962. That laser provided a coherent light source that could allow interferometric methods to be developed. Then the invention was announced or proposed by Ye Cummins, Professor Cummins, back in 1964. That was a significant breakthrough in terms of fluid mechanics measurements. The method makes measurements non-intrusively and in situ. Up until then, and even post the invention of the LDV, pedostatic probes and hot wire anemometer probes were typically inserted into the flow to make measurements. But when you start putting objects into the flow field, you're actually measuring something other than the actual flow due to the material interference by the probe. The velocity measurements of this device have been shown to provide high accuracy and good precision. There's no calibration required. The only calibration is to determine the beam intersection angle, and that can be done relatively easily, and it doesn't change over time. So one calibration at the supplier or the factory is sufficient. It has a very small measurement volume, and that can be actually controlled quite easily with proper optical design, and that provides high spatial resolution, which is ideal for turbulence flow measurements. It is capable of a very high velocity range. People have measured creeping flows, blood flows, and flows up to transonic and supersonic, and we actually are involved in hypersonic flow measurements. And as an aside, my classmate at the University of California, Berkeley, who was from IIT Madras, was one of the early adopters of the method, and he actually used the method in curved pipe flow, simulating the blood flow in the aorta. So Dr. Agarwal was one of the early people working in this field. The one non-elegant part of this method is that it requires particles to be dispersed in the fluid to scatter light. So as I said a little bit earlier, the instrument is actually measuring particle velocities, not the fluid velocity, but the assumption is that the particles track the continuous phase flow and provide a reliable representation of the flow field. By now, the method is highly developed and refined, but we still continue to develop the components as new technologies come on board. We have now DPSS lasers, which really were a big advance over the earlier argon ion gas lasers, and they have much higher coherence, so we can change the optics or refine the optics, and then the electronics and computer power has just advanced enormously. So we're doing more of the processing, as you'll see later, in the computer, given its the extreme power that these modern desktop computers have. Well, what are the key advantages? And I like to point these out because I think they're critical or important to understanding the method. The measurements are based on the wavelength of laser light, and that light wavelength is known with extremely high precision and accuracy, and it doesn't change over time. So it's an ideal measurement scale for a number of measurements, not only fluid dynamics, but particle sizing, surface speeds, vibrations, etc. Signals have a sinusoidal character, which makes them easy to detect, especially in the presence of noise, and we'll discuss some of that as I proceed with this presentation. The method can be configured to simultaneously measure all three velocity components, and it forms a direct measurement of the mean velocity and velocity distribution, allowing one to obtain mean velocity and turbulence intensity, Reynolds shear stresses, normal stresses. The high spatial and temporal resolution allows detailed turbulence measurements, as I mentioned earlier. Before I get into the description of the method, I thought I'd show you a photograph of a typical LDV instrument to give you an idea of what it is we're talking about. These newly developed instruments use compact DPSS lasers, so the transmitter system with all the optics can be built into a single package. And for this transceiver system, not only is the transmitter in there, but also the receiver with the detectors. So in this case, with a transceiver configuration, the beams are directed out into the flow, and then light scattered by particles at the beam intersection is detected back into the same lens and directed towards the photodetectors. So it's a convenient package, but I'll also provide some critique of that approach later on when I get into optical configurations. Whoops, sorry. To understand the method, you need to understand light interference. The LDV method is based on light scattering interferometry or light scattering interference. And so I'll just remind you of the characteristics of interferometry. To obtain interference, we need to have a single wave or single frequency coherent light source, typically generated by a laser. But now I have to show this or refer to this diagram down below. That diagram was from a description of Young's experiment, and Young was the first to prove the wave nature of light. And of course, he didn't have a laser in those days. He used a normal light source through two apertures, but there was sufficient coherence to produce interference fringes. But these days, we have the ideal source, an intense beam of light that's highly coherent. So it makes these interferometric techniques much more easy to develop. The light must be linearly polarized, and the polarization must be parallel. So the E vectors must be parallel and have a single polarization. We cannot get interference if we have, for example, circular polarization. To get ideal interference, we need equal or nearly equal light intensities. And so on the right here, I've shown some diagrams of light waves that are going to interfere. For constructive interference, if the light waves are in phase, we'll get addition, so we have a strong intensity interference. And this shows up to our eye as a bright line or a bright fringe. Remember that light frequencies are on the order of 10 to the 13 hertz, so it's impossible for any detector to measure these frequencies. But interferometry, of course, allows us to use the method. When we have the light waves out of phase, we get destructive interference, and so there's a dark zone, and that'll be seen a little easier on the next slide. Here I've shown a very basic LDV optical configuration just for this description purposes. We have a laser beam with intense coherent light. A beam splitter means to split the beam into two equal intensity beams, and a transmitter lens that takes the light beams, focuses them to a crossover, and that forms the measurement volume or the interference fringe pattern. Particles passing through that region scatter light to the photodetector, and that scattered light produces the Doppler signal. So at the crossover, and we've actually photographed this interference fringe pattern by magnifying the sample volume, projecting it onto a distant wall, and that pattern shows the interference fringes, the bright where we have constructive interference, the dark, destructive, and so on. When the particle passes through that pattern, it generates what we refer to as a Doppler burst signal. And that signal has a Gaussian envelope, which is due to the Gaussian intensity distribution of the laser beam. And the modulation frequency, which we call the Doppler component of the signal, is due to the particle passing these bright and dark interference fringes. The critical parameter for LDV is the fringe spacing, and we refer to that as delta. And delta is easily calculated knowing the laser wavelength, which is highly defined to many significant figures, and the beam intersection angle, gamma, which is shown here. So delta is equal to lambda over 2 sine gamma over 2. We take the measured frequency over here, which we'll do with our electronics, multiply that times delta, that gives us the velocity. I've just shown a simple cartoon or schematic of the beam overlap, and just to give you an idea of how the interference occurs. If we have two waves, where the crests of the waves combine, we have bright intensity shown in that interference photograph on the right. And when they're out of phase, of course, we have the dark lines. We can get the spacing from a simple geometry, knowing the wavelength and the beam intersection angle, which is gamma over 2 on this little triangle. That results in that expression for the excuse me, for the fringe spacing. So you're going to ask, well, where does the Doppler effect come in? Because so far we've just got a fringe mode. Why don't we just call this a fringe velocimeter? The Doppler shift is another way of describing the process. And we all know from our basic physics that, for example, if you have a locomotive blowing its whistle when it's approaching you at high speed, the frequency of that whistle sounds, has a higher frequency, I should say, than when the locomotive passes and is going away from you. And a similar frequency shift effect happens at optical frequencies. So in this case, we have our two intersecting beams and a particle passing through the intersection. There's due to that passage, there's a velocity component along beam 1 in the direction of propagation, and a equal and opposite velocity component along beam 2 opposed to the light propagation direction. From a basic understanding of the light waves and frequencies, the frequency of light is just the light speed divided by the wavelength. And what we're looking for is the difference frequency. Realize that the light frequencies are extremely high, 10 to the 13 hertz, so there's no way to measure them. So in this equation, we have the light speed plus the velocity component against the beam minus the light speed minus the velocity component along the beam. When we difference that, the light speed drops out, and now we have an expression with just the velocity. And if we look at this expression, frequency times that value there, which happens to be the fringe spacing, it's identical to our fringe model. So both models do the same job. They provide the same answer. Typically, the purists believe that the Doppler shift model is more elegant or more rigorous, but they really provide the same result. And this approach, the fringe approach, is much easier for people to understand. When particles pass through the interference fringe pattern, they'll produce Doppler burst signals, idealized in these diagrams. And because of the Gaussian intensity distribution, you'll have a whole range of signal amplitudes. You'll also have a wide range of signal amplitudes due to a range of particle sizes. Fortunately, with the LDV approach, signal amplitude doesn't matter. The measurements are based on the frequency, and so it's really a very strong feature of this method that we really don't care about amplitude, except that amplitude matters in terms of signal-to-noise ratio. If the amplitudes are too low and the background noise is high, it will be difficult to process these signals, and I'll get into talking about that later. Another characteristic that needed to be resolved was the directional ambiguity of the measurements. In my work at NASA, I was working in transonic and supersonic turbulent boundary layer separation. In those flows, you could have velocities of 300 meters per second in a positive direction, and in a few millimeters or less lower, you could have negative velocities at 100 meters per second. The problem is that if the fringes are stationary and the particle passes through it, a particle going in the downward direction will have the same signal as the particle going in the upward direction. So that leads to an ambiguity. Shown on this plot, if we have a velocity that's positive, we could have a positive frequency, but a negative particle will have the same frequency, and so there's no way to resolve that, except if we introduce a frequency shift. So we have a mechanism, which I'll show you in a moment, that, that causes the fringe pattern to move by shifting the frequency of one of the beams. So that offset frequency shown here is typically about 40 megahertz. And so now when you have negative velocity, the resultant frequency is less than the frequency shift. And if you have a positive velocity, the resultant frequency is greater than the frequency shift. So that problem's solved, and that's what I had to do in my work way back 5 decades ago at the NASA Ames Research Center. Just a quick description of the device. We typically use Bragg cells. They're acoustic optical frequency shifter. The device consists of a piezoelectric crystal that drives a compression wave into an appropriate glass crystal. Lead molybdate is one possible crystal that is used. And so we have this compression wave running through the crystal, and the beam is introduced at the Bragg angle into the crystal. One beam, part of the beam is diffracted and shifted in frequency by 40 megahertz. That's due to the interaction with this 40 megahertz shift. So that diffracted beam gets 40 megahertz imposed. And the other beam is unmolested. It essentially comes through at the same frequency. But when we mix these two together, we combine them to form that sample volume I showed you earlier. We have fringes that are moving at 40 megahertz. So that gives us that directional certainty. When we process the Doppler signals, we typically use a high-pass filter to remove the Gaussian pedestal. So what we're doing is taking the Gaussian pedestal, which we're calling this envelope, and removing that to produce a symmetric signal. And it's that symmetric signal, which we call the Doppler component of the signal, that we're going to base our measurements on. These signals arrive randomly because the particles are essentially Poisson distributed, so the signals will similarly arrive in a random fashion, and they'll have a whole range of sizes. And the objective is to detect when there's a signal there, send that information over to the processing means to determine the frequency of the signals. Well, not all signals are so ideal. In my work at NASA, we had to use very small particles. The speeds were very high, and with window contamination and so on, the signal-to-noise ratio wasn't always optimum. In fact, it was generally difficult to detect and measure the signals. So what I've shown here is a simulation of a background noise and low quality, low signal-to-noise ratio signals. And the object with the early systems that I used at NASA, we would have to set a actual voltage threshold to not detect the noise, but to detect a signal. Well, that required a lot of patience and not a little amount of frustration, because the signal-to-noise ratio and the signals would always be changing, and so you'd have to continuously adjust the threshold so as not to detect a lot of noise, which eventually the electronics will throw out, but it can tie them up and you'll miss actual good readings. So with that frustration and the importance of signal burst detection for LDV, our electronics engineer, who's a very brilliant guy, came up with a really good idea. He based the detection on the signal or the sinusoidal character of the signals. So if you look at these signals, and unfortunately the simulated noise looks like it has some periodicity, but typically background noise is white noise, a random collection of superimposed frequencies. But when there's a signal there, the Doppler part of the signal is superimposed on the noise, and hopefully the strength of the signal is enough to show the sinusoidal nature, and that is what our electronics engineer developed electronics to sample and detect. The fortunate part of that method, and we currently use it, is it requires no adjustment. So now adjusting the threshold is history. People don't have to do that or go through that or endure that frustration anymore. And the strength of the method, and we've tested it on simulated signals and real signals, is it reliably separates signal from the noise. The method is based on making 10 million decisions or detections per second, which is actually incredible. We're using short Fourier transforms, and our electronics engineer worked out a method to perform those short Fourier transforms at this incredible rate. So no part of the incoming record is missed with this device. So how does it work? Here I'm showing a typical or a reasonable Doppler signal filtered and some background noise. And what we have is a analog to digital 1-bit sampling system. It's sampling the record continuously at a very high rate. And so when there's noise, the sampling shows essentially random structure. But when the signal appears, now we get into a reasonable square wave, and the detection means recognizes that as a bona fide signal, sets a gate, and transfers that information to the higher level signal processing means using the discrete Fourier transform. So it's a very effective means for detecting noisy signals or detecting signals even in noise. And as I said, we tested this signal or this method with very noisy signals. And for example, in this case, this signal is close to 0 dB. We're still able to detect, even though it's somewhat random, we're able to detect it. And if there's enough periodicity in there, the system sets a gate and again sends that over to the higher level processing. And the higher level processing then analyzes that signal, determines if it meets certain validation criteria. If it doesn't, it's rejected. But typically, the discrete Fourier transform is very effective in hunting down and analyzing and extracting frequency from noise. And so the detection means has been an amazing advance for LDV. I'm sure you're all familiar with the Fourier transform. The Fourier transform essentially is applied to periodic signals, and it takes the signal, for example, in the time domain and transfers it to the frequency domain, and then the inverse transform takes it back in the other direction. The fast Fourier transform algorithm has been used and is well known, and it's extremely efficient in performing the discrete transform calculations. With modern computers, we can do these transforms very, very fast, 50,000 per second. Frequency measurements, because we're using analog to digital converters to sample a continuous signal, we're essentially discretizing the signal. We're taking it in little slices, albeit at a very high speed. So in fact, what we're doing is using the discrete Fourier transform to make a replica of the signals, and then the signal frequency is determined from the sampled signal using the discrete Fourier transform shown here. Now that's a complex math process. The I here is the imaginary unit. I squared is -1 for those of you who are familiar with complex math. And the sampled signal for our systems, we actually sample in quadrature. Quadrature is another way of saying complex values. So in quadrature, which is basically detecting a sine wave and cosine wave of the sampled signal, we correlate that with a cosine and sine to locate the signal frequency. And I'll show you that in a graphical representation. I always find that seeing a simple graph of the mathematical equation is always helpful in understanding exactly what's going on. Here again, we have the actual high-pass filtered Doppler signal, and we sample with 1-bit analog to digital converters. Since there's only one frequency of interest in our individual signals, 1-bit sampling is sufficient. And in fact, it's very efficient since the record we have to save essentially ones and zeros. There's no really good reason to use higher quantization of these signals. In other words, to record the actual signal shape. There's not much more information that we're going to extract out of it. But we do have a great advantage of just storing the ones and zeros, so we can store long records without occupying too much memory. Now, to find the frequency of this signal, the discrete Fourier transform simply takes and correlates a whole range of sinusoidal frequencies, essentially multiplying it times the sampled signal. So it starts at 0 frequency and increases the frequency in steps until at some point the sinusoidal frequency is very close to the sampled frequency. And in that case, the real and imaginary components show a strong product or power, and in the power frequency power spectrum, we get a strong peak. And that peak helps us or leads to defining the frequency of the signal. If you had noise superimposed on this signal, we might have some other samples in between. That noise would not correlate very well with our sinusoidal signal or our sinusoidal approach here. And if we have noise, what you'll have is a distribution of the noise along the power spectrum, but with adequate signal, that noise will be well below the power in the peak frequency or the signal frequency. So we've developed that approach into our advanced signal analyzer. We call it the ASA. And this device uses an advanced form of the discrete Fourier transform. And we've shown that it improves the performance up to 100 times that of the earlier counter processors. At NASA, in the early days, we just had counter processors to find the signal period. And they were subject to noise, so we really had to struggle for good quality signals to make reliable measurements. Some of the features of the ASA, the high-speed ADCs can sample up to 500 megahertz to record the signals in quadrature. So that's a real and imaginary components. The Doppler signals, which we know vary in time due to the differences in particle velocity. Again, at NASA, we had velocities from 0 to 600 meters per second in a separated flow region. So the length of the Doppler signal, the transit time through the probe volume, is going to vary significantly. So we need to record a high number of samples to capture the entire signal for each and every particle passing through the probe volume. We've actually have a capability of sampling 100,000 ADC readings, and that's well above what's needed. But some of the ideas are to have, for example, continuous signal with high seeding so that we can get turbulence frequency spectra out of the measurements. And so that capability is built into our system. The signal processing, DFT, is computed in a high-speed computer using software. The earlier FFT or DFT-based instruments generally used electronics-based processing. For example, they would use a digital signal analyzer, and those devices were very fast, but they were kind of fixed. They had to be programmed in one fixed state, and so that was limited to measuring or computing DFTs of a fixed number of samples, and didn't provide much flexibility. Our approach was to sample the signals and condition and sample the signals, and then send those signals over to the computer. Well, 20 years ago, when we started this out, computers were quite slow, so we were not very competitive, or not as competitive because of the processing speed. But as computers have advanced, their software processing is now much faster than the digital signal analyzers or the electronics-based processing. So that approach is used in this ASA, and it provides a much greater flexibility. We can use advanced signal validation. It's easy to upgrade as we evolve our techniques and procedures and validation schemes. It's easy to send out an upgraded software version, and so your system is always up to date. And we've shown that the method is very reliable in terms of discriminating signals from noise and providing high resolution and accuracy. And just to go back to that comment I made, the signal duration will vary, and I show a factor of 2 or 3, but in many cases it can be as much as a factor of 100 in duration. And so that requires the potential for measuring over or sampling the signal over a very long and differing lengths. And we know from the theory that signal sampling time directly affects the measurement precision and accuracy of the measurement. So it's important to process the entire signal. Once again, the earlier Fourier transform instruments would use a fixed record length, no matter how long the signal duration was, and that really compromised the performance. And this just shows a screen from our software for the ASA processing. With software, we can display any number of components of the processing scheme, and it allows the user to readily interrogate how well the instrument is doing and how well the device is set up for making reliable measurements. In this case, we're showing the real and imaginary sampled signals, the computed power spectrum. You can see it's relatively low noise, so you can see the side bands easily here. And there's just a low noise background with the power spectrum very well defined, allowing very accurate frequency measurements. We also digitize with high quantization ADCs to basically provide information on the measured signal, in this case, to ensure that we captured the entire signal and we're able to get an optimum processing of that information. Well, I'm now going to turn to configurations of the optical systems. And just over the many years and from our competitors, there's always a degree of confusion as to how these systems should be set up for making optimum measurements. I went through that whole process at NASA, and of course it was very early in the development of the method. In fact, we were some of the first to make high-speed measurements. Many people believed that the method couldn't possibly operate at those high speeds. But it took some experience, or required some experience, in understanding the method and optimization of the optics and the optical configuration. So I'm showing here 4 possible optical configurations, and I'll go through each of them to kind of give you my point of view or share my experience as to how these will perform. I've also shown in the inset here a schematic of the sample volume. When you have 2 beams focused and intersecting, you'll form an ellipsoidal volume. So where the beams fully overlap, you get complete interference. Where they are partially overlapped, you'll get a DC component, no interference, and then a DC component. Not ideal, but you can make measurements with particles passing through that region. Generally, we like to define our measurements to just the region where the fringes are well defined and complete. So in my selection process, the preferred location is what's called off-axis forward scatter. So we have the transmitted beams coming out of the transceiver or transmitter in this case, and we locate the receiver off the beam axis. There's a number of reasons for that. One, when using an aperture in the receiver, it only allows light scattered from the central part of the beam intersection. The other advantage is that for boundary layer measurements especially, you're close to surfaces and laser beams will cause a lot of flare light from those surfaces, and the particles are not scattering very much light, so they can easily be overwhelmed. That scattered light can easily be overwhelmed by flare from other objects in the near field. So being able to move our receiver, and I should point out that it doesn't have to be in a particular plane. This receiver could be anywhere in a conical position away from the transmitted beams, or it doesn't matter in which plane, normal or outside of the beam intersection that the receiver is located in. The advantage also is that the scattering efficiency is quite good in a near forward direction. So this is what I consider optimum configuration. What people who have limited experience in the method will prefer is the transceiver approach, where the beams are transmitted out of the package to form the sample volume, and the scattered light is detected back through the same optics into the receiver optics. Well, it makes a nice convenient package. Alignment is easy. It doesn't, where you point the beams is where the signal is going to come from. And so it's attractive, but it has a number of deficiencies or problems. One is that the sample volume is not well defined, so you're essentially observing over this entire ellipsoidal region. That isn't a problem necessarily, except that these fringes will tend to flare. They're not completely parallel, so they'll tend to flare a bit. And so if you can avoid measurements of particles outside of the crossover, you'll have less systematic error in your measurements. The other problem is that any flare light from the surface is going to compete with your signals. And in addition, when you pass laser beams through optics out the same optic as the received light, there's inevitably some scatter from those surfaces, and that again competes with the signal. So only when necessary would I use this approach. The number 3 position is a direct forward scatter. This provides the most efficient collection of light. The forward scatter light is most intense, so you get a strong signal, but again, the definition of the sample volume, the effect of the fringe flaring a little bit compromises the measurements, and also being able to reject flare light from surfaces is not optimum with this configuration. And number 4 is off-axis backscatter. And the backscattered light, here we get a better definition of the sample volume, but the scattered light intensity is still not too efficient. So I'll show you that in this slide. And what I've done here is I've calculated the light scattering using Lorentz mean theory, which provides essentially an exact representation of the scattered light. And I've done the calculation for a 1 micron particle, and the laser wavelength is 0.532 microns, which is generally the green laser beam used in these systems. Particles, index of refraction, not that significant, but this would be typical of a seed particle index of refraction. Note that the ordinate is a log scale, and I've used arbitrary units because the magnitude, absolute magnitude, is not important. I only want to characterize differences with scattering angle. So scattering in the forward direction, which is that direction, that's forward scatter, provides a very high scattering intensity. It's essentially dominated by the mechanism of Fraunhofer diffraction, and so it's the most efficient in terms of light detection, but again, definition of the sample volume is the problem. So I prefer being off axis, in this case at 20 degrees, but I've lost about half the scattering efficiency, 800 to approximately 400, but it's still adequate signal strength. Now we'll go to position number 2, which was the backscatter approach, the transceiver approach, and that's not too good. The light scattering intensity is almost 100 times less than the near forward. In fact, it's a little over 100 times. At the 20 or 30 degree position, or sorry, 10 or 20 degree position, it's about 100 times. So if you're getting or if we could get adequate signals with a 100 milliwatt laser with this scattering arrangement, we would need a 10 watt laser to get similar signals, and that's actually impractical. So there again, that's why I insist that, if possible, use an off-axis forward scatter detection configuration. Now, some fairly easy descriptions here. For a two-component laser Doppler velocimeter, we need 4 beams. And remember or realize that the direction of velocity measurement is in a plane parallel to the plane of the beams. So for the green beams, we're actually measuring this velocity component. And for the blue beams, we're measuring the velocity in their plane. So that gives us 2 orthogonal velocities in a single plane. We can then take the 2 velocities, combine them to get the actual velocity vector. Fairly easy. For 3-component velocity measurements, we need to configure our second transmitter with 2 beams. Usually we're using different wavelengths to separate the signals for the different components. We typically will use a yellow for that component, and we have to orientate that transmitter so that a velocity component is measured along the bisector of the other 4 beams. So we need to get that velocity vector. So in this off-axis arrangement, we'll get a component in that direction. So that gives us all 3 velocity components. And then based on our, or my earlier discussion here and our experience, we typically set up a 3D system in this type of arrangement. We'll have the 2D transmitter at 30 degrees off the axis of the receiver, and the 1D transmitter 30 degrees opposite to it. So what that provides is a receiver with detecting scattered light at 30 degrees from the forward direction for these 2 pairs of beams, and from that pair of beams. We have color separation optics in the receiver, and that's used to separate the various velocity components. Well, we need a significant angle or a substantial angle between these sets of beams so that we can get a reasonable resolution on that velocity component along the bisector of the 2-component system, so we get all 3 velocity components. Well, in this case, clearly we don't have an orthogonal set of vectors, but our software is designed to easily transform the velocity measurements at these different directions into a laboratory coordinate. So it's quite easy to get that transformation done. All right, the less than elegant part of the LDV method is the need for seed particles in the flow. The particles must be added because that's where the scattered light is coming from, and they're the little messengers, or I like to call them the flow transducers, that are providing information on the flow behavior. These seed particles must be small enough to adequately respond to the flow to measure mean velocity and turbulence. And again, in my early experience with high-speed flows, that's a very demanding requirement. Seed particle concentration distribution should be uniform, or measurement bias will occur. And I know of many cases where the experimenter has seeded the local flow because he doesn't have enough seed delivery capability. And by seeding locally, if you have velocity excursions from a high particle concentration region to a low concentration, you're going to bias because you're going to report a lot more readings from when there are more particles than when there are less. So that's a danger, and as I say, I've seen that in publications. Considerations for seed particle selection. Well, size. We need to know the mean and the distribution. Generally, people report, well, I have 3 micron or 5 micron particle size, but typically sizes are not mono-sized or monodispersed. They have a distribution, and very often the skewness of that distribution has a tail out into larger particles, and those are the particles that are actually being detected and measured. So that's a caution that needs to be observed. Excuse me. If the particles are too small, of course, you won't get any signal-to-noise ratio, so you compromise the measurement of the particles. If the particles are too big, you compromise the measurement of the flow. You get good signals, but poor responsivity to the flow fluctuations. And material density is important because the inertia of the particle is really based on its mass. So when I say size, I really have to add in the density of the particles because, like I said, it's the inertia of the particles that's important. There's a number of means available for dispersing particles in flow facilities, and I'll talk about those in a moment. One of the problems I had at NASA is we were seeding the flow with atomized oil, and the problem you have is that the oil eventually deposits on the walls of the wind tunnel and the windows, and that leads to many stoppages and many window cleanings. Well, seed material possibilities. We can use water drops from a simple atomizer. A room humidifier works for certain applications. Those devices generally produce mean-sized droplets in the 0.5 to 5 micron range, but again, they'll show a tail out to maybe 10 or 15 microns, and so one needs to be careful that that isn't the particles that they're getting good signals from. The problem with water atomizers, the water evaporates, and so if you have a closed return wind tunnel, for example, humidity will increase, and there's other attendant problems with that. To avoid evaporation, we can use mineral oil or other light oils from atomizers, and again, these generate particles in a suitable range. Incense smoke has been used. It's a very inexpensive, easy to apply method, and of course you can even have a religious ceremony to go along with it. We have alumina particles have been used, but they're difficult to dispense. They're dispensed in a fluidized bed, and typically one uses a cyclone separator to separate out the large aggregates or agglomerate and just deliver the small particles to the flow. We use polystyrene latex spheres at NASA. The PSL are dispersed in water and sent out as a fine spray, again, using a simple atomizer. The water evaporates and leaves the 0.5 to 3 micron particles. And it turns out polystyrene latex spheres, you can easily get them. They're the basis of white paint, for example. So we would just dilute white paint by several orders of magnitude and disperse the paint and atomize it and deliver that. The particles were generally in the 1 micron range and fairly narrowly distributed, which made them attractive for our application. Smoke can be formed by heating oil, again, similar size. Heating and condensing glycol called fog juice has been used. We use that in some applications. That approach is used, for example, for theatrical applications. If you have a play and you see the fog drifting around the set, that's fog juice. And so it's not harmful and easy to disperse refractory seed particles. We need to have refractory particles if we're measuring high temperature environments, including combustion flows. I'll just run through a few particle generation means. At NASA, I built atomizers, essentially Laskin atomizers. You have a tube and a pressure vessel. The liquid would climb up the tube due to the Bernoulli effect, blowing high-speed air past a small orifice. The liquid would come out, pre-film, come out, be blasted by the jet and atomize. And then I had a cyclone or a strong vortex in here to strip out the larger drops and just deliver the smaller particles to the flow field. There are a number of commercial devices available. Our partner, LaVision, has several particle generation means. It's a small, lower delivery system. They also have high pressure, high rate of delivery devices for seeding these various applications. I want to say or describe a little bit about particle response. If I had more time, I would spend another hour talking on this subject, because we have spent a lot of time concerned with the particle response in various flows, and especially high-speed turbulent flows. In this particle response equation, we have the mass of the particles, the velocity, or the response rate of the particle, how fast or how rapidly the particle velocity will respond to the new condition, and that's equal to the drag on the particles, the drag force, and the drag force is dependent upon the difference in the gas phase velocity and the particles. We can simplify this equation. We're going to assume, or we have to assume, or we can assume a relatively small slip velocity, and for these small slip velocities, the particle Reynolds number will be small enough to enable the use of the simple Stokes flow drag coefficient, which is 24 over the Reynolds number. And here the densities, the density of the particle, density of the gas, and dP, of course, the diameter of the particle. If we make that substitution, we can get this response relationship. The rate of change of the particle velocity depends on the density of the gas to the density of the particle. This is usually a fairly high ratio. The particles have much higher density than the gas. It's inversely proportional to the particle diameter squared, and depends on the difference in the gas phase velocity and the particle phase velocity. Now that's kind of a interesting equation to look at. The restoring force for a particle moving into a new environment with a different airflow velocity is the difference in the velocity of the gas and the particle. So as the particle arrives at the new or approaches the new flow velocity region, this value becomes very small, so the restoring force gets very small. In a turbulent flow or an accelerating flow, there must always be a particle lag, that is a difference between the gas phase and the particle phase, to provide that restoring force to get the particles to respond to the next acceleration. So when someone says, I don't believe my particles are lagging the flow, I think they're representing the flow well, you have to question that and say, well, they're not responding completely to the flow, but what we really need to do is keep the particles small enough so that difference remains relatively small. And haven't got time, or didn't have time to really go through all of the long developments of these response conditions, but I thought it'd be worth just showing you some of the key results. I'm limiting the diameter to a range of particle sizes that would be suitable for LDV measurements, 0.5 micron to say 5 microns. And it's interesting to note that the response time, the characteristic response time, is approximately 2 orders of magnitude difference. So to get good particle response for turbulence, it's really important to keep the particles as small as possible. And of course, the stopping distance at even a slow 10 meters per second is significantly different. For 1 order of magnitude difference in size, it's 2 orders of magnitude in stopping distance. That just happens to be that d squared behavior. I spend a lot of time also on analyzing the response of particles to turbulent flows. We need to remember that turbulent flows have a continuum of length scales and time scales from large scale eddies down to the Kolmogorov microscales. The large scales are typically defined by, for example, a jet diameter or boundary layer thickness or some other scale in the flow. The Kolmogorov scales are the very small scales as the turbulent eddies break down. It's the Kolmogorov scales where the turbulence energy dissipation occurs. So what I spent my time on was to determine what the largest particle would be that could adequately respond to the various turbulence scales, the Kolmogorov or small scale turbulence, and the large scales. And I did that for a range of Reynolds numbers. Well, with 8,000 Reynolds number, about a 0.5 micron particle will respond to the Kolmogorov scale. So that's getting down to the limit where one might easily make measurements or make reliable measurements with an LDV. The large scale can be handled by about 5 microns, and hence that's why I've been showing seeding devices that send out particles or disperse particles in the 0.5 to 5 micron range. At higher Reynolds numbers, the response requirements for the Kolmogorov scales are getting quite small, and realize that the light scattering for these submicron particles goes as the diameter to the 4th power and even to the 6th power as we get down to much smaller particles. So the scattering intensity is minuscule, and it's unlikely that you'd be able to make reasonable measurements from particles of that size. So you really won't be able to resolve the Kolmogorov scales. For the large scales, we can still make adequate measurements with 2 micron particles. So you might say, well, that's an interesting analysis. How well does it work? With the development of the phase Doppler interferometer, we're able to make particle size and velocity measurements simultaneously. In fact, part of what drove my invention of that method was the idea that if we could measure the particle size simultaneously with the velocity, I could discriminate out particles that were too large from my turbulence flow measurements and hence improve the reliability of the measurements. Well, in this case, we have a free jet. It's a sonic jet, and the Reynolds number is about 30,000. I'm showing here the velocity measurements, individual velocity measurements, versus the particle diameter. And I looked at about 0.7 micron size particles all the way up to about 15 microns. The collection of samples has a high population here because that was the kind of size distribution of the atomizer that we used. And that's the point I made earlier, that you have to be careful when you claim a certain size for an atomizer. you may have a large population of relatively small drops, but you're going to have some large drops out on the tail, and those may be the ones you're measuring. But getting back to this, the turbulence fluctuations shown here for the small particles seem to capture the turbulence intensity, so that those fluctuations in velocity are representative of the large-scale fluctuations or the turbulence intensity of the flow. As we move towards larger particles, those fluctuation velocities are suppressed. These particles are not responding to the high velocity excursions in the flow. So using a larger seed particle, you're not going to get very good turbulence measurements. So how well did we do? Well, my prediction for around 30,000 Reynolds number is somewhere in the middle here, which would be about 3 microns. And here we have 3 microns. So my predictions weren't that bad. They at least are in the proper range and are probably adequate in defining what particle size is needed given the Reynolds number of the flow. The LDV system generates or it measures individual particles at a very high rate. In this case, we had a 3,000 particle per second range. Typically, we can get to tens of thousands of readings per second, and those measurements help us generate a histogram of the velocity distribution. And that's shown here for the channel 1 and channel 2 velocities. But I want to point out that in our systems, we do not use these histogram data or the bin widths to calculate our statistics. We're actually using the actual measurements, velocity measurements for each particle, which is a little better resolution than binning the results and then computing the mean and standard deviations. So with that, we can look at turbulence measurements. Generally, turbulence measurements are reported in terms of a mean and fluctuating velocity component. And I've shown here a continuous record of a fluctuating velocity measurement for a turbulent flow. And what you'll see is the mean is fairly stationary, and on that there are fluctuations. With the LDV approach, well, first of all, with hot wire anemometers, which was the earlier and still used method, you get a continuous reading of the turbulence fluctuations, so you get a direct time average and time response. With the LDV method, you're discretizing the record, so you're actually sampling at random, albeit very short intervals. You're getting samples as each particle arrives, and if you have a high seeding rate, you're going to discretize. It's a difficult word to say. We're going to discretize the results and form a pattern which simulates the continuous velocity fluctuations, but it's not identical. But for statistically stationary systems, which these are, the ensemble averages, which is produced by the LDV, are equal to the time averages, and that's considered as an ergodic ensemble. So for the mean velocity, rather than getting it from the continuous measurement, we can get it from the discrete measurements of the velocity. And similarly for the standard deviation and the cross-correlation components, which are the Reynolds shear stresses. Well, we've come to the end of the technical discussion, but I would like to just describe some of the various optical systems that are available in the configurations. This one we saw earlier at the beginning. It's the transceiver system, and of course I provided a fairly negative indication of this, but in some cases it's essential, and with the sufficient laser power, these diode pump solid state lasers can produce up to a watt of power, which is a lot of power when focused down into a very small probe volume. So it is possible to get good backscatter measurements. In fact, we do quite often have good results with these instruments. When the flow field requires very small particles, then it becomes a little bit more challenging. Most often, we configure our systems as a transmitter, separate transmitter, and receiver, and that allows the user to position the receiver in some optimum collection direction and get proper measurements. And it also can be used in the off-axis backscatter direction if the flow axis demands that. Shown here also the signal processing devices and, of course, the display of the histograms. We provide 3D LDV and phase Doppler systems. This 3D system consists of a 4-beam green, blue, 2 green, 2 blue beams transmitted from one transmitter, the yellow beams from another transmitter set off at those plus or minus 30-degree angles that I described earlier. And the receiver is set at the bisector. So we're getting good signal quality and equivalent signal quality from the beam pairs because we're sampling near or relatively near to the forward direction. Now, aligning these systems is not very challenging. We typically set an aperture at the focal volume, direct all 6 beams through that aperture, and then the scattered light from the aperture is directed or aligned into the receiver. We provide high quality traversing systems so that you can traverse the flow field with very high resolution to get boundary layer profiles or velocity measurements around various flow bodies. We've also built large-scale systems with very large optics, both transmitter and receiver. In this case, measurements were made with a working distance of about 3 meters from the optical head. And it's a fairly large-scale wind tunnel. The receiver is over off screen to your right. If the flow field is fairly large, then it's almost inevitable that you need to place a more compact, streamlined LDV system within the flow and traverse that system within the flow, not being in close vicinity of the point of measurement so that you're not getting flow disturbance. But to get adequate signal-to-noise ratio, it's a lot easier to have a smaller system within the flow. We provided a off-axis backscatter system to Moscow University. In that case, they were looking at automotive and architectural wind flow studies. They had a model of tall buildings, and they were concerned about wind flows and vortex shedding causing motion of the buildings. And so they have a very large-scale wind tunnel that they needed to penetrate from one side. There was a wall on the other side, so they were really forced into using this backscatter approach. We also have a confocal backscatter system here where the beams are transmitted out of the same package, and we have a large reflector Cassegrain type collector that collects the scattered light, takes it into the detectors. The advantage of LDV systems is you can configure them in a whole range of sizes from very large to very small. Now, either these are very large pencils or the optics are quite small. In fact, these systems are provided by MSC, a company formed by my classmate at Berkeley. He worked with me directly, then he worked with me at NASA, and then he was an employee later he started out his own company, which is quite successful. And MSC is also represented by Tescorn. So this system was designed for water flow measurements. It's immersed in a water tank, so you can make measurements around various hydrodynamic bodies. This system is I believe is a 2D transceiver type system, very small, very short working distance, but for certain flow fields, it's ideal. We've provided a number of LDV systems to university. This again is Moscow University. They were doing fundamental flow studies in a small wind tunnel. So the graduate students were applying the method for fundamental studies and also basically aiding in their learning and development of fluid mechanics understanding. We've made systems for industrial applications. In this case, we needed to make measurements in this pipe flow, and these types of configurations are relatively challenging. In this case, we have a perspex pipe with a relatively thin wall, but nonetheless, when you direct a beam through a cylindrical surface, the beams are going to be deformed and the intersection angle changes somewhat, which we had to compensate. And similarly with the received light going through this optical surface is going to degrade the image of the sample volume. But nonetheless, we were able to make reasonable measurements within this facility. So in summary, I emphasize that the LDV is the most reliable and accurate means for measuring flow and particle velocity. In some cases, we're just interested in, or we're interested also in the particles. But for flow measurements, it's still, I think, the most productive instrument and the most accurate. The device requires a coherent light source, but those sources are readily available with the development, especially of the DPSS lasers, these very compact diode pump solid state lasers are excellent for this purpose. They have very high coherence and now very high intensity capability, up to a watt or more. The method allows us to measure mean and fluctuating velocities in highly turbulent flows. It has a very large velocity range capability, up to hypersonic speeds. It doesn't require calibration after manufacture, which makes it very convenient for the user. You don't have to worry about annual calibration shipments back to the manufacturer. The modern lasers, electronics for signal processing, and computers have really allowed us to approach turnkey systems. In fact, some of our systems are indeed turnkey. The complaint of these methods has often been that they're difficult to use or difficult to understand. And so we're trying and expending a good deal of effort in making these instruments easy to use, and by setting them up automatically, it really facilitates better reliability. We're not counting on a graduate student to make a blunder so that you have to repeat an experiment, for example. And finally, the method has been the basis for the phased Doppler interferometer, which I invented back in the 1980s. And hopefully sometime in the near future, I'll be able to present a webinar on that method. So thank you very much for your attention, and I'm open to any questions or discussion.
Thank you, Dr. Bassalo. We have a few questions. First, can this method be used for fuel flow in spacecraft propulsion system?
For fuel, sorry, please repeat.
Can this method be used for fuel flow in spacecraft propulsion system?
In the
spacecraft propulsion system.
Oh, spacecraft.
Yeah.
Yeah, there's no reason that I can think of why you couldn't do that. We have used this approach, and I'm not quite sure I fully understand the question, but if the spacecraft is in zero gravity, there's really no problem. And if you're measuring fuel flows, for example, to measure the fuel feed to the combustor, I think I don't see any reason why that wouldn't be possible. Of course, you always have to worry about optical access to the system. One of the requirements for these optical diagnostics is you have to get the light beam in and you have to get the scattered light out. And so you need to be able to see where you're going to measure, because that means that the light will get in.
Okay, we have got another question. Is this method useful to dense spray?
That's a very good question. We have expended countless hours on dealing with dense sprays, and we recently have published a paper on that subject for dense sprays, and that would be more related to the phase Doppler interferometer than the LDV. The condition is, one, the light beam must be able to penetrate into the spray field. If the spray is so dense that the light is extinguished, then no, you can't make the measurement. But if the beams can penetrate in and the scattered light can get out, the other problem is having more than one particle reside in the sample volume at a time. And so we've recently addressed that problem with what we call signal parsing. So even if there's more than one particle in the sample volume at a time, we can discriminate each of the particle signal events and measure several particles, or as many as 2 or 3 particles in the sample volume. So that isn't an issue. If the spray field is so dense, I've often suggested that to get the beams in, you might have to shield part of the path up to the measurement volume so that the beam isn't extinguished. Both the beam and the scattered light aren't extinguished. So those are strategies that we've used to cope with that problem. But that's a very good question.
So we have another question. Does fringe gap depends on droplet diameter to be analyzed?
Please repeat that.
Does fringe gap depends on droplet diameter to be analyzed?
I'm not sure I understand that. The fringe spacing?
Yeah, the fringe spacing.
Yes. Again, that's more in the realm of phase Doppler interferometry, and yes, the answer is yes. The fringe spacing needs to be adapted to the droplet size range that one wants to measure. And we, in our systems, our phase Doppler systems, we actually have software-controlled mechanisms within the transmitter where we can actually change via software command the fringe spacing to accommodate a very wide range of droplet diameters.
Okay, so we have another question. What are the additional requirements to convert a PDI system into a LDV for airflow measurement, and what flow frequency can be resolved with 90% amplitude matching?
Well, the first part of the question, to convert the PDI into LDV, that simply means turning off the particle size validation. If the particles are not spherical, for example, the sizing approach, the phase Doppler part of it, may reject the readings. But if the particles, the seed particles, are spherical, there's really no reason to turn off the sizing, because as I mentioned, one of my motivations was to be able to measure the particle size so I could discriminate large particles that wouldn't follow the airflow and confine my airflow velocity measurements to the smaller particles that have the proper responsivity. Now, please ask the second part. I didn't quite hear it.
Okay. The second part is what flow frequency can be resolved with 90% amplitude matching?
I'm not sure how the amplitude matching comes in, but the flow frequency that can be resolved, I'll attempt to answer that. It depends on two things. One, it depends on the seeding rate. So if you have sufficient seed, you'll have a high enough data rate to resolve the frequencies in the flow. But with that said, one might suggest that the Nyquist criteria held. So if my sample rate is not twice the frequency I want to resolve, I might have aliasing. But when you have discrete sampling, then the problem of aliasing doesn't occur. And so you can actually take a long enough record and you can resolve relatively high frequencies due to the random arrival of the particle events. And I'm not sure about what the amplitude comment or question was. I don't quite understand what that is.
So there's another question.
Yep.
How to deal with random time-space velocity data, whereas we need equally time-space velocity data to calculate turbulence spectra?
You don't. People have addressed this problem over the past 4 decades, and if the questioner would like to send a request through you, I could possibly locate technical papers. But again, it comes down to if you're sampling at a uniform rate, then you must meet the Nyquist criteria. But if you're random sampling, you're not going to get aliasing. So if your sample for a long enough record, you can then come back and use that information to resolve relatively high frequencies in the flow. And again, Bill Mayo, who is a contemporary of mine, did a lot of work in that area back in the 1970s. And so if there's a strong interest in that capability, I would be happy to search those papers and send copies.
Okay, we have a few more questions. Okay, is spray required seeding particles?
Again, I'm sorry, my hearing is not so good, so you'll have to repeat.
Is spray required seeding particles?
Spray.
Does spray required seeding particles?
I don't think I understand what the question is. You're saying this? Does the spray require seeding particles?
Yes.
Oh, well, maybe I can address that possibility. If I had a spray flow and I was interested in the two-phase characteristics, in other words, I want to measure the gas phase turbulent fluctuations with a dispersed phase, which would be the spray. I want to measure the gaseous fluctuations. Then I would probably want to seed, unless the spray drops are small enough, I would probably want to seed that spray with very small particles that will respond to the gas phase turbulence. And we've actually done that many, many years ago. And so, yes, if you want to get turbulence frequencies, if you want to see if there's coherent structures in the spray and the spray breakup, then seeding the local gas flow will allow you to get more information on the gaseous phase turbulence or the continuous phase turbulence.
So we have a lot more questions. And,
gee.
we'll be preparing a questionnaire document and we'll be sending it to everyone across who have attended this webinar.
Okay, I would be happy to give written questions or written answers.
Okay, great. Thank you, everyone. We appreciate you being here. Please feel free to contact us if you have any questions later. Thanks again for joining us today, and we'll see you next time.
All right. Thank you very much.